Audience, we have two real heroes of chemistry with us today. One of them is Peter Mahaffy. He did his PhD in chemistry at Indiana University and joined King's University College in Edmonton in 1981, where he's presently the co-director of King's Center for Visualization in Science. In addition to being the past chair of IUPAC's Committee on Chemistry Education, he's also the past chair of the International Council on Science Committee on Freedom and Responsibility in Science, and of the temporary working group on education and outreach for the Organization for the Prohibition of Chemical Weapons. The organization of PCW incidentally won the Nobel Peace Prize in 2013. His current research and professional works in the interfaces of chemistry education, visualization in science, sustainability in green chemistry, and responsible uses of chemistry. Alain Krief is both Tunisian and French in origin. His scientific interests are tied to the higher idea of strategy in both chemical synthesis and in the global chemical enterprise. He attributes some of this to the influences of great chemists that he's worked with, such as Gilbert Stork and E.J. Corey. Dr. Krief is presently the Executive Director of the International Organization for Chemical Sciences and Development that is headquartered at the University of Karachi. He's also an emeritus professor at the University of Namur. He's published hundreds of research publications on novel synthetic methods, synthesis of small bioactive products, markably in pyrethroid insecticides, selenomethionine, and in antiviral compounds. Many of these compounds have been commercialized by leading companies, especially in the area of HIV/AIDS with Janssen and Johnson & Johnson Company. So with no further ado, I will turn the floor over to Peter.
Thank you very much, Joe. We begin our webinar today with a provocative assertion, and that is that the practice and overarching mission of chemistry needs a major overhaul if it's going to be fit for purpose in the 21st century and beyond. That assertion is made in a recent commentary in Nature Chemistry, and I'm delighted that Alain Krief, one of the authors of that Nature paper, is co-leading the webinar. For this presentation, instead of using the term overhauling, I've chosen the title Reimagining Chemistry to emphasize the creativity and ingenuity that we're going to need as a professional community in order to substantially reorient towards systems thinking. The American Chemical Society vision statement aspires to advance for the benefit of Earth and its people. And all of us as chemists know that chemistry has a remarkable track record of doing that over the past 2 centuries. We've learned how to understand properties and the behavior of substances. Chemistry has been an important platform for the developing of many other molecular sciences, and we can all think of diverse applications that have improved the human condition: medicines, agriculture and food, plastics, energy, clean water, and materials. So chemistry for the benefit of Earth's people? Absolutely. Without the contributions of Haber and Bosch to the industrial synthesis of ammonia, which is sometimes referred to as making bread from air, and the required developments in the field of catalysis, perhaps 40% of the world's population wouldn't be here today. But 7.4 billion people also create multiple unfolding global challenges. And that very same Haber-Bosch process that's responsible for keeping 40% of human beings alive is perhaps a good example of a failure of using systems thinking about the life cycle of ammonia and the consequence of introducing too much fixed nitrogen into our planetary system. If one would look at 100 nitrogen atoms in the form of ammonia fertilizer that we produce, and if you happen to be a vegetarian, 86 are wasted and only 14 end up in your mouth. And if you're a carnivore, the numbers are even worse. 4 end up in your diet and 96 of them are wasted. Let me suggest, in the context of the Nature paper, 3 ways in which we might assess the nature, the magnitude, and the urgency of those multiple unfolding global challenges, so that we can then begin to explore how our chemistry-informed imagination might better be visibly focused on addressing them. The first is the UN Global Goals for Sustainable Development. Chemists know how fundamentally important chemistry is in addressing each of these sustainable goals. Can you imagine tackling hunger, health, provision of clean water and energy, or climate change without vital contributions from chemistry? But do we have the imagination to make achieving these goals in 14 short years, 2030, a vision priority for the chemistry profession and for chemistry education? And a second lens with which to see those multiple unfolding global challenges comes from an interdisciplinary science initiative to guide human development on a changing planet. It's called the Planetary Boundaries Initiative. It was first put forward in a paper in Nature in 2009 and then updated substantially in 2015, with a lot of the work being led by scientists at the Stockholm Resilience Center. And the initiative provides a science-based analysis of the risk that human activity, human perturbations, will actually destabilize the Earth system at a planetary scale and perhaps raise the question of whether Earth is still a safe operating space for humanity. The analysis distinguishes between thresholds and planetary boundaries. A threshold might be considered a tipping point, a place with respect to a control variable. You might imagine that to be something like carbon dioxide concentration in our atmosphere, where we pose such a threat to an Earth system that we reach a tipping point. A planetary boundary is set as the value, the numerical value in most cases, of that control variable that keep us at a safe distance from the threshold. Color coding indicates where we are with respect to these 9 boundaries. The ones that are shown in green are boundaries where we are still below the boundary. An interesting example brought up in the paper is stratospheric ozone depletion, where we've actually crept back away from the boundary. Some others are approaching the boundary, ocean acidification. Several are in the zone of uncertainty, shown in yellow, climate change, land system changes. 2 of them are beyond the zone of uncertainty. One of them relates to that Haber-Bosch process that we talked about. In the latest paper, 2 of these boundaries are set as core boundaries. And these are boundaries that are capable on their own of triggering very substantial to our planet. Do students leave our chemistry courses at the secondary and post-secondary level knowing how to use the fundamental knowledge they've gained in chemistry to identify a safe operating space for humanity on our planet? And a third measure of the way our world is rapidly changing, with implications for how chemistry needs to be reimagined, comes from our colleagues in the geosciences. Fundamental measurements of chemical and other parameters in our biosphere show exponential change, often beginning in about the past 60 years. Put these changes together, and those measurements suggest an unmistakable and an unprecedented human imprint on our planet. Do we have the imagination to make knowledge of those changes a visible, urgent priority for the chemistry profession and for chemistry education? The geoscience profession has taken on those indicators, and an international scientific group's been working for 7 years on the subject, and they recommended just 2 weeks ago to the International Geological Conference meeting in South Africa that the magnitude of those human-induced changes are so evident and so large that we should reset the clock on our planetary timescale, the geologic timescale. Their recommendation, which still has to be acted on, is that Earth has now entered a brand new epoch called the Anthropocene epoch, an epoch defined, in fact, by human activity. And in a paper earlier this year in Science, the evidence for the work of that working group of scientists is presented. We're currently in the Holocene epoch, and if you look at the reason why for the last 12,000 years human life has flourished so well, it's because we've lived in a period of stable temperature, the temperature changing by less than about 1 degree Celsius over 12,000 years. How do we measure those changes? We measure it with chemistry, the ratio of heavy to light isotopes of water in ice core back into deep time. And the evidence is presented in that paper that we now have reached an abrupt transition, a transition that's measured in soils, in sediments such as these Greenland glacier tills. It's also measured in evidence of activity that began in the 1950s, above ground atmospheric nuclear testing, depositing radionuclides on our soils and in our oceans. Let me turn it over for a question.
And here is our first poll. We'll give you a few moments to select the right answer.
Thank you very much, audience. I think the responses suggest that perhaps we have some work to do in the world of chemistry education. If we're going to address these multiple unfolding global challenges, do they require, as suggested by the Nature paper, an overhaul of chemistry? And I'm going to turn this over now to Alain Krief, who's going to tell us a little bit about IOCD, and then we'll summarize some of the key conclusions in the paper.
Thank you, Peter, for providing me the opportunity to discuss about what we have done. The paper of One Word Chemistry and System Thinking was an initiative of a group of 4 chemists working with the International Organization for Chemical Science in Development, IOCD. It is our vision that we want to advocate and to share for the future of chemical sciences. We believe that chemistry must go beyond being a science, embrace being a science for the benefit of society, and chemists should include chemical problems and solutions in complex interconnected systems. They should also propose sustainable and ethical issues. IOCD was established at UNESCO in 1981 and is an international NGO based in Belgium. It has been headed by 2 Nobel Prize winner presidents, the late Glenn Seaborg from US and the present Jean-Marie Laine from Strasbourg in France. We have been working to promote the application of the chemical science for human development and economic growth, and in the current decade, our strategic focus has been in 3 interrelated areas, focusing on chemistry for better health, chemistry for a better environment, including the very important aspect new material for cleaner production, storage and use of energy, for which we have a strong group at the University of Montreal working in this area, in capacity building in chemistry education. We have also very strong relation with African Academy of Science in Kenya. Thank you, Peter, for providing me this chance to be with you today.
Thank you very much, Alain, and I hope that you'll be able to join in on the questions at the end. And so what this IOCD initiative has done, some of the key ideas in the Nature paper are to call, as Alain mentioned, for systems thinking, chemistry being a science for the benefit of society. A triple role is seen for chemistry, creating new scientific knowledge, translating knowledge into useful applications, and the commentary suggests that we've done a pretty good job of both of those things in chemistry so far. But a new imperative is put out, and this is where the metaphor of overhauling comes in, that we need to do some things very differently to meet the emergent challenges of multiple unfolding global crises. Some implications are outlined for industry, for chemistry practice, much stronger basis in systems thinking, including life cycle analyses, consider chemistry in its interconnected systems, pay attention to human and animal health and their relationship to biophysical parameters and the boundaries of our planet, and a very special responsibility for chemistry in meeting the UN Sustainable Development Goals. Education doesn't get off the hook either. Implications for chemistry education to be reoriented, to focus on a science for the benefit of society. Pedagogies need to change with an emphasis on problem solving, a systems perspective, and teaching chemistry in contexts, not just the context of applications, but relevance to society, contribution to meeting global challenges and fostering cross-disciplinary working. So if we think about that challenge put out in the paper, are there good examples of how systems thinking can transform chemistry? And I'd like to walk you through a few because we do have some examples and we can build on them. Going back to a Canadian initiative in 1985 from industry, Responsible Care, a commitment to not only being perceived to act responsibly, but to act responsibly. Followed by the initiation of green chemistry programs by the US EPA and the formation in 1997 of the ACS Green Chemistry Institute. So green chemistry and engineering, the premise is to go beyond simple concerns about hazards from toxicity to include systems, chemical and engineering systems, energy conservation, waste reduction, life cycle considerations, sustainable and renewable feedstocks. And I won't dwell on these, but many of you are familiar with the green chemistry principles. To try to get this systems thinking into the practice of chemistry and engineering, reaction efficiency, efficiency metrics, renewables, catalysis and recycling, process efficiency, life cycle impacts of chemicals, chemicals in the environment, and chemical hazards and exposure. ACS Green Chemistry Institute has a couple of interesting initiatives, both in industry and in education. One of them is the establishment of industrial roundtables, like the Pharma Roundtable, whose mission is to catalyze the implementation of green chemistry and engineering in pharma industry globally. Strategic priorities to inform and influence the research agenda, to define and deliver tools for innovation, promote education and training, and enable global collaboration. A paper was published back in 2007 that highlighted some of the key research challenges keeping pharma from being greener. And the purpose was to do an assessment and then to motivate academic research in the areas of practical need. And one of the ways that the GCI Pharma Roundtable picked up on that was to start a grant program, which has been very successful, leading to about $1.8 million in grants and publications that have been cited over 2,000 times, which are getting at the greening of processes and reactions used in the pharma industry. The GCI also produces reagent guides and solvent selection tables, which are useful not only to the pharma industry, but in both industrial and academic settings. A recent initiative just last year that emphasizes systems thinking in the practice of chemistry was a group of 30 scientists and professionals from 24 countries. We met at the OPCW in The Hague to develop ethical guidelines for chemistry professionals, particularly as they relate to the mandate of OPCW and keeping the world free of chemical weapons. The starting point is that the responsible practice of chemistry improves the quality of human life and the environment, but we also recognize that chemicals can be misused, and some of the serious ways in which they can be misused are in the production of chemical weapons, such as we've seen again just in the last couple of weeks in Syria with reports of chlorine gas, a beneficial substance, being used against civilians. The core guideline is that achievements in the field of chemistry should be used for the benefit of humankind and the environment. The key elements you might want to look at a little more closely, dealing with sustainability, education, awareness and engagement, ethics, safety, health and security, accountability, oversight, and the free exchange of information. And these are not intended to be a new code, but elements that can be incorporated into existing codes and new ones to align with the provisions of the Chemical Weapons Convention. This has subsequently been endorsed by IUPAC. So we have emerging systems thinking in chemistry. Is it comprehensive enough? Is it fast enough?
Time for our second poll. Which response do you think is right?
As I was thinking about this question myself, is it comprehensive and fast enough? I took those two initiatives that I've mentioned, Responsible Care, 1985, the establishment of green chemistry in 1993, and I superimposed them on the Keeling curve, this measure of the control variable of carbon dioxide for one of our most important planetary boundaries dealing with climate change. At the time of our webinar, we're now up over 400 parts per million. The planetary boundary for climate change, measured in terms of concentration of carbon dioxide, is 350. And so we've continued this march to perturb the energy balance of our atmosphere that supports life on this planet. I think there are things that we need to do to move ahead more quickly with respect to emerging systems thinking. And I think this poses a particular challenge for chemistry education. We need to reimagine chemistry education so that if we were to carry out this webinar 5 years from now, that survey that we took at the beginning might be answered just a little bit differently. Chemistry for the benefit of Earth and its people. I think those of us who are chemistry educators are able to understand that when we teach a course like general chemistry, We can see the landscape, we can see the systems, we know that the content that we're presenting is going to lead to an understanding of how chemistry can benefit Earth and its people. But there's quite a bit of evidence in the research literature that students have a different perspective. Students in courses like general chemistry see the road ahead looking something like this. Facts are isolated. They have difficulty transferring learning to new problems, connecting ideas to life. We use pedagogies of transmission, not engagement, too frequently. Emphasis on memorization and algorithms. And perhaps we put too much emphasis on training future chemists and less on equipping citizens to be able to see how chemistry relates to important systems. I want to leave you now with 4 examples of some emerging systems thinking very quickly in chemistry education. The Green Chemistry Education Roadmap, the ACS GCI, an initiative that we've undertaken at my university to think about course level goals and learning outcomes, and a research project that has come out of that. And then finally, a new project that we're proposing for the International Union of Pure and Applied Chemistry. So the Green Chemistry Education Roadmap is an initiative now that has been underway for a couple of years. It involves stakeholders in both industry and academia. The idea is to bring the community together to try to figure out how we can fully implement green chemistry education, sustainability education into chemistry that we teach. And the roadmap is intended to define and clarify the needs for green chemistry education, and we hope that this will result in clearer learning objectives and assessment, increased impact of teaching efforts, and greater opportunities to engage in green chemistry education. The second initiative is work that we've done at my own university, as we've thought carefully about what we do, particularly in general chemistry, but in our chemistry program, to formulate learning outcomes. And I think a key to embracing systems thinking in chemistry curriculum is to articulate learning outcomes for students that in fact explicitly address the things that we want them to take away from chemistry courses that go beyond content knowledge, skills and techniques, and this triangle of thinking levels that we, I think all as chemistry educators know that we want to emphasize. And as we started to articulate what some of those other things are, thinking about this from a systems perspective, we've come up with quite a number, and we're now trying to embed these goals into very specific learning outcomes. And one of the most important goals, if we think about those multiple emerging challenges, is to equip our students, those who are chemistry majors, those who aren't in general chemistry, for complexity and uncertainty. An approach that has some promise, I think, in dealing with complexity and uncertainty, systems thinking, addressing multiple unfolding global challenges, is teaching learning from rich contexts. And I use that term to describe particular implementations of case studies, context-based learning, that provide deep and rich opportunities for learning diverse concepts through contexts, and that require really that our students use higher order cognitive skills to connect concepts and apply the knowledge gained to new contexts. That's what systems thinking is really all about. In our implementation, we make the motivating context the starting point. It's not atoms first, it's contexts, global challenges first, and then we develop the scientific content for students so that they, on a need-to-know basis, are equipped not only to understand the content, but to deal with these important challenges. And the first work that we've done on this, an international collaboration funded by the National Science Foundation with partners involving the American Chemical Society, Purdue University, Iowa State University, has been published recently in the American Chemical Society journal, Sustainable Chemistry and Engineering. If you would jot down vc3chem.com, you can look at the resources. We started this by mapping the core curriculum in chemistry and understanding what we wanted to communicate about climate literacy. So the rich context we had selected was a sustainability context dealing with climate change. And then we went into the research literature to understand what it was that our students know about those chemistry concepts and what they get mixed up. The same thing with the climate concepts. From those, we developed learning outcomes that were articulated as what we know, why we know it, why do we believe what we believe, and why should a student care about a particular learning outcome. From that, we designed interactive materials, we assessed student learning, revisited our tripartite learning outcomes, and then disseminated this to chemistry educators around the world. I thought I would give you just 4 examples of rich context concept questions that we can start with that nurture systems thinking in students. So rather than starting with atoms and bonds and molecules, start with questions that relate to climate science and sustainability. How do we know what the temperature on our planet was 800,000 years ago? Instead of just ideal gas law, which gases support life by regulating the energy balance of our planet? For acids and bases in equilibria, how does atmospheric carbon dioxide influence the pH of the ocean? And for thermochemistry, how is the way we power our planet altering Earth's balance? And by developing interactive materials that work through these questions, we're able to get at an understanding of the climate change planetary boundary, the 2 different control variables that are used to measure it, either the concentration of carbon dioxide or the energy imbalance at the top of our atmosphere relative to the beginning of the Industrial Revolution. And ocean acidification, we introduce concepts related to acids and bases and equilibria, precipitation, and here are a couple of references that you could take a look at later on that tease out those important chemistry concepts and mathematics and relationships and calculations along the way toward obtaining some understanding of that very important problem of ocean acidification. And my last example is a new initiative that's only about a month old, and we're hoping to gather some momentum for an initiative that will help us include systems thinking, multiple unfolding global challenges in our learning objectives and assessments. And so we're preparing a group that will put together a proposal for an IUPAC project across countries to develop program learning objectives that are based on systems thinking, with the overt goal of helping the next generation to guide human development on our rapidly changing planet, to borrow the title from the Planetary Boundaries. We know that chemistry educators don't make change easily. The group has suggested that we also recommend change strategies for implementation and look at the literature and see what works. And we know also that if these are to be taken up, learning outcomes, the assessment of those outcomes is incredibly important. And so we need to connect with those who are developing program accreditation standards and incorporating these into standardized exams. So let me end with a few acknowledgements. I'd like to thank ACS for putting on this webinar, and particularly thank Jenny McKellar from the Green Chemistry Institute, who brought us together for this webinar, but who also provided some of the slides that you saw on the work of the Green Chemistry Institute. Alain's co-authors on the Nature paper, Henning Hopf, Stephen Matlin, and Govardhan Mehta, and then the research team that put together the Visualizing the Chemistry of Climate Change material, and our co-authors on the publication that I referenced for you, VC3 Chem. If you'd like to take these ideas further, the first chapter in a recent publication, Chemistry Education Best Practices, Opportunities, and Trends, might be helpful, and several other chapters in that book also address specifically global challenges that we face and how chemistry is playing a role in addressing them. And on Alain's initiative with his co-authors at IOCD, they have entitled this initiative One World Chemistry, and you can go to oneworldchemistry.org for some further details.
Thank you. Audience, I'm combining a few questions here with kicking off our questions with one for Alain. Please, could you discuss for us a few specific examples and some of the great successes and some of the more difficult challenges with using systems thinking to examine large strategic initiatives?
Yes, we have discussed in our Nature paper, and I will briefly mention 3 different aspects of systems thinking. The first is chlorofluorocarbon. The second is climate change, and the third is antibiotic resistance. Historically, very important and clear example where systems thinking proved to be vital was the case of chlorofluorohydrocarbon, CFC. In the 1920s, innovative chemists developed volatile SFC and very stable compound, apparently very inert chemically and biologically. They found immediate application as refrigerants and in aerosol propellant and firefighting. Decade later, the new analytical tool of electron capture detector became available, and evidence was found that the SFC were accumulating in the atmosphere. Later still, people in completely different field of science began to study the depletion of ozone layer in the upper atmosphere, especially over the polar regions, and also to study the photochemical behavior of FFCs in atmospheric conditions. Then a link began to appear, and the world realized that FFC were causing mounting atmosphere damage that could expose the whole surface of the planet and its population to the harmful effect of UV radiation that ozone helps to filter out. Fortunately, the entire world was sufficiently alarmed by the dangers to take swift action and agreement on the Montreal Protocol in 1987, which led to the phasing out of FFC. One of the leading US diplomats in the negotiation for the protocol commented that it exemplifies our growing understanding of the need to bridge traditional scientific discipline and examine the Earth as an interrelated system of physical, chemical, and biological processes. It was a clear example of what we say now, system thinking, and it has been very successful. Now, if you look at the two other cases, global warming and antibiotic resistance, this seems to be a complete failure. You have heard about global warming, discussion, but we never reach an agreement on both the need to reduce greenhouse gas emission and how the burden of responsibility will be shared between states. And the solution still doesn't go far enough, so there will be a rise of probably 3 degrees above the pre-industrial level during this century, and no one knows what will happen, or we can imagine what will happen. Finally, if you look at the antimicrobial resistance, IMR, widely used antibiotic is another very instructive example. This problem has arisen because we have massively overused antibiotics, both in human health and in animal farming, and have allowed antibiotics to drain into the environment, which has created resistance in microorganisms. Well, this biological time bomb was evolving, there has been also a market failure in which the incentive for pharmaceutical company to develop new antibiotics sharply decreases, and there have been no new class of antibiotic brought to the market in the last 30 years. In this case, lack of attention to multiple interlocking systems has meant that we are now in danger of running out of antibiotics with major consequences for human health. So these are 3, but there are many others that we can discuss. But these are the 3 which we have discussed in our Nature paper, and which mean that 1 was successful over 3 important ones.
Very good. Now I'll address the next question to Peter, and this one is coming from Robert Schmidt and a few other people. So what is suggested here in switching to systems thinking is a huge switch with an unprecedented level of public education that's needed and a huge shift in collective human behavior. And it isn't even so much that people don't believe, for instance, in global climate change, but that they may not be aware of it or that they haven't changed their behavior. And so please address some of the big problems about engaging a larger part of the population on this.
Thank you very much, and that's an excellent and a challenging question, Robert. There are two ways that I would get started with that. One would be all of the citizens who are the ones who need to, in fact, be informed, who will be making political, economic decisions in the next 50 years as our planetary boundaries either control variables continue exponentially on or begin to reach a state where we're guiding human development in a more responsible way. Those citizens are first, at some point in their lives, students. And so the formal education system, starting in K through 12, but then continuing into universities, plays a very important role in their education. And I think a very encouraging development in the United States is the initiative to create next generation science standards, where students in the K-12 system are in fact being asked to embrace systems thinking. Compartmentalization of science is no longer enough. And so students now entering our colleges and universities are going to come in with that kind of thinking already in their background in the elementary and secondary system. And then I think we need to pick up on it in colleges and universities. We need to be educating not only chemists, but we need to be educating scientists and non-scientists in formal educational settings about chemistry and its interconnectedness. Informal education, education of the public, is also incredibly important. And so a lot of the work at my King's Center for Visualization in Science is in fact directed exactly at that. There's an International Year of Chemistry Legacy project, explainingclimatechange.com, that sets out to explain some of the underlying science of climate change to the public, and to do so in a way that doesn't simply leave us wallowing in despair, but empowered to know that the actions that we take can in fact make a difference. I think chemists and chemistry educators need to take on that challenge of educating the public and also educating our students about these new ways of thinking.
Well, given that answer, I'm actually going to address the next question to Alain from Charlene Jett. And it's an interesting way of thinking about it. Is it wrong, though, to go back in time to think about when things were less heavily processed, for instance, using wax-coated paper containers for milk? And there's the added comment, plastic milk and juice containers just drive me nuts.
Yes. Well, okay, so the plastic problem is another case where we have produced a large amount of plastic who are now all over the world, all over the sea, and we don't know what to do and how to destroy them. Fish are eating them, birds also, and we have no understanding officially of what we have to do. It's already too late. Of course, there are new initiatives to have biodegradable plastic, but it will take probably several hundred years to solve the problem. And maybe, of course, it would be good to have to return back to other kind of can that plastic one. But economically, they are very useful, and so I don't know how the community will manage it to do that. It is not only money, but it is the survival of many species.
Thank you. And now I'm combining a question from Patrick Julian and Bev DeVore-Wedding for Peter about the integrated curriculum. So the comment here is, look, I've been teaching in high school an integrated curriculum for over 20 years, but I understand that that's not usual at the university level. Others at the university level embracing systems teaching. And another personal comment comes in here. I think that more tours of places that exemplify systems such as water plants, garbage dumps, hospitals, with corresponding explanations of the chemistry that's going on would really help.
Thank you very much, and thank you for that question. When we take on our responsibility as chemistry educators, whether it be at the elementary, secondary, or post-secondary level, we take on a commitment to try to equip our students to be professionals, but also to be citizens that can act responsibly. And I know many of the students in university classrooms, they just want to pass chemistry, they want to get a degree and they want to get a job. And it can be hard to reach them with these systems-oriented approaches. But I think the biggest challenge isn't with the students, it's with me, it's with professors, it's with colleagues who lack the imagination to see how we can integrate the teaching of content that we know we need to teach from these rich contexts, from these systems that are incredibly important for us to equip our students to address. And the jobs that our students are going to be looking for as college or university graduates are jobs that are changing. Our planet is changing very, very remarkably. We simply look at those control variables for the planetary boundaries to get a sense of that. And I think increasingly the jobs that are going to be available to our graduates are jobs that are going to require that they be able to apply the content knowledge they're learning in particular areas across disciplines as part of teams and toward local, regional, and global challenges. In many ways, I think elementary school curricula and high school curricula, particularly with the NGS standards in places like the US, are leading the way, and I think we need to learn as college and university professors from those experiences.
Very good, thank you. And a question now for Alain from Sleeto Sumalong. And so students then learn these things, then they work for industry, and the processes are run by the untrained, and industry is managed and owned by the unbelieving. Where does that leave us? What now?
One of the aspects is I feel that chemists has to invade other field. They don't have to stick to chemistry. They have to have their knowledge, but they have to go to the knowledge of the others. And they have to include that. Not to be only chemists doing chemistry, but a lot of things that can include chemistry in the system and also make new jobs. Now, industry is related to profit, but when you teach, and when you teach, for example, a reaction has a good yield, what does it mean? Yield is related to economics. If you look at little waste, is also economics. So what I believe is if you use the modern approach, you will go to better economics, and that means that people working in industry has to be educated, first of all their life, and they have to apply the new thinking when they do and they work. Maybe the boss could not be aware of that, but all people have to be aware, and it should be very important that it goes from top to bottom and from bottom to top, and people discuss that matter. Anyhow, 20 to 30 years ago, using chiral catalyst was almost useless. Nowadays, industry, especially perfumery, are using that very consistently.
Joe, could I pick up on that just a little bit?
Please, but I would love to add just a little corollary in here before you do. So a question from Paulina Pine says, so in addition to what we're discussing with this, please also address a little bit about changing the fear of chemistry by some proposals regarding high school chemistry teaching.
Thanks very much. Let me just chime in a little bit on Alain's suggestions, which I think are very good ones. That first question is really a question about how we bring about change. And bringing about change requires strategies, awareness of successes, best practices, both in the world of industry and the world of education. I think increasingly it's becoming very evident from the education of consumers that consumers are beginning to require that the products they buy are products that are made responsibly, that are made with life cycle analysis. And so it's becoming more difficult for companies to create products that don't in fact involve sustainable and systems thinking. They are becoming less profitable. There are some interesting models for industry that we can look at, something like the B Corp in the US, where the responsibility for university degrees that do continue to include all of that important content knowledge in chemistry, but also that set out as goals and assess our students on how they think systemically. Then we're beginning to move that bar. And one of the challenges along the way is in fact very evident in that last question. There is a fear of chemistry out there. And perhaps in part there's a fear of chemistry out there because chemistry hasn't very visibly been seen as addressing global challenges, including challenges related to health and toxicity.
Thank you, Peter. Now, both of you, we're almost out of time, so I have to ask you for just a few quick thoughts about the highest take-home message from each of you as we finalize today's webinar. Peter first.
I think what I'd like to leave with everybody on the webinar is to catalyze some thinking, coming together as a community to think a little more carefully for each of us how we can use systems and sustainability thinking so that these powerful tools of chemistry we have as professionals and educators can perhaps help our planet and its people groan a little less and sing a little more.
And I apologize to the dozens of you who put in questions that we can't answer. But Alain, for your final thoughts, please.
I think that chemists should include in the solution of the chemical problem the thinking that it is not so easy, that we have to look around us very properly, to have a strategy to start research or to sell a product, and to understand that any of our action can be, after some time, very good or very poor, and that it could be too late every time. So we have to think much more, and for that purpose, chemists have to go abroad chemistry to have a vision and a knowledge of many things that they are not aware of. Finally, education has not moved a lot from the 80-60, and we have to envisage new type of education that the children, especially at school, could be very involved and very happy to learn.
Thank you for watching this presentation. ACS Webinars is provided as a service by the American Chemical Society as your professional source for live weekly discussions and presentations that connect you with subject matter experts and global thought leaders concerning today's relevant professional issues in the chemical sciences, management, and business.